Hello, hi. In this video, we are going to see how to generate a PWM signal using STM32 microcontroller. So, before diving into the STM32 microcontroller, what are the prerequisites? Like, we need to understand what we need to generate. Like, here our requirement is PWM, and what is a prerequisite for it. Like, there are basic calculations, very simple things. Not more than 2 calculations are required, but that much understanding is required, I think. So I am just going through it, because PWM is a very commonly used signal, and that too STM32 offers very good clock frequencies of the order of 80 megahertz, 100 megahertz also. So even 20 kilohertz, 200 kilohertz, very high frequency PWM can be generated using STM32. So to exactly get our desired PWM frequency, what are the calculations involved, and what are the simple code lines or lines of code that you need to include, that I'll be showing, and also showing you the output of our STM32 controller. That's the PWM. So mostly the frequency and duty are what we are going to control while generating a PWM. So what are the calculations we should know? So before going into the calculations, we should know 2 parameters. Like, one is the clock frequency and what is the PWM. So let us assume few values right now and go forward. Suppose if I assume the clock frequency of my controller is 10 megahertz. Okay. The clock frequency of my controller is way larger than 10 megahertz. It is around 80 megahertz, but I am assuming it to be 10 megahertz right now, because we are just starting the calculations, and we can change these values and again calculate the actual thing also. That's not a problem. So let me say my frequency, the clock frequency, this is the microcontroller's clock frequency is 10 megahertz, and I want to generate a PWM that is of 100 hertz. That is nothing but 1 kilohertz PWM that I want to generate. This is my requirement, let me say. So what are the calculations we should do? And first let us look at our PWM. The PWM is this signal that is a pulse kind of wave, which has a fixed T on and fixed T off, and total T on and T off together is a time period, and that is given as T. Here to generate 1000 hertz frequency, what will be the time period? Time period will be 1 by f, so it is going to be 1 divided by 1000, which is nothing but 0.001 second. 0.001 second. So that will be our time period of our PWM, that is one cycle of the pulse. Okay, so now this is my requirement, everything is clear. So let us move, let us still further move down. So now is the actual calculation going to come in. The first thing that we need to calculate is after setting the clock frequency, the first thing we need to calculate is the effective clock frequency. What is effective clock frequency? Effective clock frequency comes after we prescale our maximum clock frequency. There is always a parameter setting called as prescaler in the timer, whichever timer you select. Here I've chosen the timer 5. So in timer 5, under the parameter settings, for each of the for each of the timers, we have something called as prescaler. So prescaler can be set different values. It allows a wide range of values. Suppose if I choose my prescaler to be 2, it's one case scenario. You can choose any value lesser than your clock frequency, but I'm choosing 2. So what happens, just to understand, let's go with it. And one important note I would like to give here is, if your prescaler value that you're choosing is 2, the value that you will be entering in the cubeide, the programmer or the interface, it will be a value lesser than just one value lesser than the actual value. Suppose my prescaler is 2, I'm always putting 2 minus 1. I don't like to put exactly the value 1 or subtracted by 1. I like to put it 2 minus 1, so I know my prescaler is 2. That is always fixed in my mind. So that's why I always prefer writing in this in this pattern, like -1, -1. Whatever is my prescaler, -1. That goes in the entry. Okay, that should be clear. So what will be my effective frequency? My effective frequency will be my clock frequency, that is my 10 megahertz clock frequency, divided by my prescaler value, that is 2. So this makes my effective clock frequency to be 5 into 10 power 6, which is nothing but 5 megahertz. So after my prescaler, or after prescaling my actual or the maximum clock frequency that I have set, my effective clock frequency has become to be 5 megahertz. So whatever calculations we are going to proceed right now will be with 5 megahertz clock frequency, or we can call this to be an effective clock frequency. Okay, the next important thing or next necessary thing to be set is the counter period. What is a counter period? Counter period is just here. I've set here as 1000. Okay, this is also a value that you are going to set. I have set 1000 just for my convenience. I can change this to be 2000 and my values will change accordingly. I can change this to be 100 and my values will change accordingly. It is a value that you are going to choose based on the higher or lower the frequency. The prescaler, higher the prescaler, lower will be the final PWM's frequency. Similarly, higher the counter period, again lower will be the frequency, but which affects most? The prescaler affects the frequency of the PWM the most. The higher you want the frequency, choose the prescaler value lower. That will be one thing that I can tell you. Okay, and you will understand once you start working on it, playing with these frequencies, you will be an expert in handling all these things, so it's not a problem. It's just for beginners, I'm just doing it. Okay, the second important calculation after prescaler is our counter period. Counter period is the total period, total length, or the total time, that how much times the timer should tick for one cycle. That is our counter period. How much time the counter should take, the timer should take for one period, and after that it will reset and again start a new cycle. Okay, that is what the counter period is. So here we have set it to be 1000 in this example. So if the counter period is 1000, what will be the frequency for what will be the final effective frequency? The final effective frequency is calculated by the effective frequency or the frequency of the PWM. This is our frequency of the PWM will be the effective clock frequency divided by our counter period. So 1000 is my counter period, so this is my value. So effective frequency would be 5 kilohertz, right? 10 power 6 divided by 10 power 3 will be 10 power 3, so 5 kilohertz will be the effective frequency. But what was our requirement? Let's go back. Our requirement was 1 kilohertz, right? 1 kilohertz was my requirement. Then why am I getting 5 kilohertz? Okay, sorry, that place we need to think here. Because I've set the counter period by myself, I had to compromise, but it's okay. My requirement is actually 1 kilohertz, so let me change this counter period value accordingly so that I will get my final value to be 1 kilohertz. So let us do that calculation. Let me say no, our frequency of the PWM is determined by the effective frequency of the clock divided by the counter period, right? So now let me calculate the counter period value based on my requirement of the frequency of our PWM. So in that way you will have effective frequency divided by frequency of my PWM. So both things are things we know. So effective frequency was 5 megahertz and the frequency of the PWM that I desire is 1 kilohertz. So this gives me 5000. So if my counter period is 5000 then I will be getting a frequency of 1 kilohertz as my PWM's frequency. I will meet my requirements. Under what conditions? Under these conditions. Under the conditions of prescaler to be 2 minus 1 or 2, actually 2, but in the written form it is, or in the entry form it is 2 minus 1, and the counter period must be 5000. If the counter period is 5000 and my prescaler value is 2 minus 1 or actually 2, and my f clock is equal to 10 megahertz. The actual clock frequency is 10 megahertz and the effective clock frequency was 5 megahertz because of the prescaler factor, and my counter period if I set to 5000, then I will get a frequency of 1 kilohertz as my final frequency of my PWM. Okay, these are the settings part. I think if this much is clear, if you're clear, then we are good to go and do our calculation. I mean, we can good to go and do our coding part. So let me open the IDE. So this is our cube IDE. I've already opened, and there is already some project already open up here, but I would like to create a new project to show you how it all happens. So file, new STM32 project, and it will take a little bit of time to initialize and all that. So only two factors I was mentioning again, the prescaler value and the counter period. Only two factors we need to be worrying about. Okay, so now this page is opened. So now I have to write my STM32 controller board's name. I'm using actually Blackpill board with STM32 F401CCU6. So let me write it in this commercial part number tab. So I will say STM32 F401 CCU6. So I am ended up with two of this over here. So the U6 is mine, so the first one. I'm selecting that and giving next. Okay, and I'm going to give this project name as we're going to generate 1 kilohertz frequency. Let us say 1 kilo PWM as the project name, and let me finish it, and it will take 2 minutes for everything to complete. So let's have patience. It itself will generate IOC file, and if we can edit. IOC is like a user interface where we'll be able to set the timers and the prescaler, the duty, and also the frequency of the clock. Actually, this offers a 80 plus megahertz. 84 megahertz I think is a maximum frequency. 84 megahertz is the maximum frequency of the clock of the controller that I'm using, but there is a flexibility that I can go and use lesser than that also. So for that, pin out and the configuration, the first page that you see, this is our board actually with all the pins they are showing. But before that, I will go to the clock configuration tab over here. The clock configuration tab, there is, you can see H clock, right, in megahertz. It is 16. I'm going to 16 is the default one, but actually maximum clock is 84 megahertz. I can go up to 84 megahertz. You can see here in this place, but I'm not going to go until 84. We are just generating a very small frequency, 1 kilohertz. So, and also we assumed our clock frequency to be 10 megahertz. So I'm going to make it 10, and here, that's it, and enter it. And it is asking like, do you want to use other sources? It will change the other sources, like this is a big block, right, accordingly, and let it do that. So it has changed some values over here, and now our clock frequency has become 10 megahertz. And now again I'm going to the pin out and configuration. The important thing is go to the timers for PWM, and I'm going to set timer 1 itself. In timer 1, let me first in the clock place I will enable internal clock, and then in channel I'm going to use channel 1, and you have to go and select the PWM for channel 1. So PWM generation channel 1. So this is what I'm done. And now coming to the parameter setting is here. To make it a little bigger, let me put it this way. So the prescaler value, as I said, let us set to -1, and the counter mode is always up, and counter period, that was important. We obtained 5000 to be the counter period to obtain a 1 kilohertz frequency of PWM. So that's all is our settings part. And before we move on, this pin view, you can see this green color, pin number A8. So it is selected pin number A8 for this timer 1 channel 1. So timer 1 channel 1 is associated with pin number A8. So now you know where you should look for the output also, pin number A8. Okay, if it's clear, let us save the code. And once you save the code, it will ask you whether to generate a code for you, and I will say yes, please generate a code for me, and it will generate a main.c code, and it is updating the code. It will again take 1 to 2 minutes. Yeah, it is done. So this is the code I've got here. All the timers would have been enabled, PWM would have been enabled. So only one timer I was using, so MX timer 1 initialization, it is done by itself. So all that you need to do is just two things. I will again go back to my one node and show you the coding part. So coding part is also pretty simple, not at all anything much for the PWM thing to be understood. Only 2 points as I've written here. It is capture and compare register is one thing that you will have to write. So let me again say that clearly. So time, because we are using this is one of the command you will be using, timer 1 CCR1. CCR1 is capture or compare register. 1 indicates the channel number because we selected channel 1, and whatever the value here we put. So what the value here we put also matters. Like we know our PWM, we have set our counter period, right? The counter period is 5000 for us. So if the counter period is 5000, this CCR1 register is for setting the T on. So whatever you set this number here, that much will be our duty cycle. So for 5000, if I set 2500, the duty cycle will be 50% because 2500 is half of 5000. So this is one line that we need to include, and the second line we need to include is the starting. You need to start the PWM. So for that we need to say HAL timer PWM start, and this is indicating timer 1, like pointing address of the timer 1 and timer channel 1. So that much will be the what we will need to do. Only 2 lines to include. So let us proceed and complete this in our code. You can include this in the while loop or in the initialization part also. Wherever you want you can write. And one more thing I would like to say before writing the code is that everywhere you can see user begin, initialization, user end. So everything that write inside such a block, start and end, that will be always unerasable. Anything you write away out of these things, out of these blocks, initialization and ending block, that are really like not safe. That means every time you save the code from IOC to here, it will be deleted. So what I mean you will understand later when you try it by yourself, but for now it is okay. Let me write. So user code begin 2 I'm starting, and I will always keep my code within user code end 2. So whatever I write inside that, even if I go back to this IOC, and because every time I make a change in IOC, I have to save it. Every time I save it, the code will be generated. So every time the code is generated, it will be rewritten. So while it is rewritten, this will not be erased. Whatever you write between these blocks will not be erased. But anything you write outside these blocks, like start and begin and end, that will be overwritten, erased. That's what I meant. So what are the 2 lines we saw? First one was timer 1, pointing out to CCR compare capture register CCR1. Not timer 10, it's timer 1, a pointer CCR1 register. Value what we chose was 50% duty cycle, 2500. And then we also wanted HAL function, HAL PWM, it was start, but in between something else was there. HAL timer PWM start, HAL time PWM start, and then we had the address of timer 1, H time 1, and then timer channel 1. So everything is fine. So we have made our settings, code also included 2 lines only, and now it's time to upload in STM32. I'm using STM link v2 programmer, and I'm uploading it to it. So this is the first time uploading this code, this project, no? So this is showing it up. So it's getting uploaded. Let's wait. Once it is uploaded, I will show you using my logic analyzer, the output. So I have my logic analyzer with me. Let me connect it. Just a minute. Just trying to figure out all the wires. Okay. My logic analyzer is here. Yeah, so it is uploaded successfully. I'm connecting my logic analyzer, opening logic analyzer software, and I'm going to start. First let me connect to pin A8, right? A8 and ground. Pin A8. So pin A8, yeah, connected to pin A8. Good. So I will start. Okay, channel 1 has some signal. Let me yeah, I've zoomed it in. Okay, and this much is okay. So now let us check, is it fine? You can see here the frequency is 908 E9. You can see here, right? Every time and the time period is totally 1.01 millisecond. So 1.01 millisecond is the time period, so the frequency would be 1 by this. It's also given the duty of 49.99%. This, I think, I hope you are able to see the duty also here, the small box. So we are able to obtain whatever you wanted here. So let us try changing something. We have kept the duty of 50%, so it's approximately 50%. Like there will be a very small band of error, that's fine. It could be because of the logic analyzer, or it could be because of the analog errors. Like nothing can be so precise, right? But STM32 gives a really good precise results. That's something. So instead of 50% duty, let us keep around 80% duty, or really close to 5,000. Let me say 4,500. It's close to 5,000. And so now the duty will be changed. Duty in the sense that T1 will be changed. Let us see whether that is happening. It's getting uploaded. Good, it's uploaded. I'm opening the logic analyzer again. Let us start it again. Stop. See, you see the difference? Now the pulse width is around 90%, so 89.98%, and the time period is same because the frequency will not change here. But if you want to change the frequency, you can still play with either prescaler or with the counter period. So if I change the counter period to be instead of 5,000 to be 1,000, what will happen? The frequency will change to 5 kilohertz. So according to our calculations, if you want to go back, we can see if the PWM frequency, if I change the counter period here to 2,000 instead of 5,000, the effective clock frequency is actually 5 megahertz. 5 megahertz divided by 5,000 would give us what? Okay, if we change right now it is 5,000, right? So if I change the counter period to 1,000, then our frequency F frequency will, the PWM frequency will be 5 kilohertz. So let us see if we can do that thing, and I'll show you that example and wind up this video. So instead of 1,000, let's keep 5,000, and again save it. Once I save the code, again the code will be rewritten. That's what I meant. So everything that is inside that block will be safe. Okay, let this be written. So whatever I've written inside the block is safe, right? Because user code begin and user code end, anything you write between that is safe. Okay, the code is there, and let me upload it into the controller. It's going. Just few seconds, it will be done. Yeah, done. And let me again open the logic analyzer. I'll start it. Stop. There is no change in the frequency. Is it 1.1 kilohertz to 5 kilohertz? Let us again review our thing. It is 4,000. Okay, I'm sorry. Now our okay, it should be not 5,000, should be 1,000, sorry, and then we will upload it. So the code is getting updated. If it's 1,000, then we cannot have 4,500 over here. The T1 should be lesser than 1,000. So for 50% duty, I can keep 500 as my T1, and I can still upload. Sorry, actually while re-editing I already changed it to 1000, and again I changed to 5000 by mistake, so that was the error, but that is again change it back. So now it is 500. So I think I hope I haven't confused you. Now again start the analyzer. Yeah, now we can see the difference. Stop it. See, now it is, you can see the frequency is 10 kilohertz. Why is it 10 kilohertz? Okay, let's go back to the calculation and check why is it 10 kilohertz. So right now I have given the prescaler value is 2, it's okay, no issues, and the counter period is 1000. Okay, if the counter period is 1000, what will be the effective thing? Counter period is 1000, so the frequency of the frequency would be let me again write it down here and check it. So let me see. So the effective frequency was 5 megahertz, and the counter period we have changed to 1000, so it should be 5 kilohertz only, right? Frequency of the PWM, yeah, it should be 5 kilohertz only. And what are we getting? That is not right. Okay, I should again reconnect it. Let me connect it again. Yeah, frequency, sorry, I've seen the wrong parameter. The width is 9k. Okay, the frequency is 4.9 kilohertz as correct, so everything is fine. I was just looking into the width and was sorry. So actually the frequency is 4.94. It's correct. It's 5 kilohertz. So the calculations are correct. So I've just showed you with 2 different settings. I hope the things are clear. And this is all for this video. Thanks for watching.